distribution was that we had our standard deviation given, right? So we're comparing a sample mean to a population mean with a given standard deviation sigma. That's a population parameter. As a recap, statistics are from a sample. That's either an X bar or an M, or it's an S or an SD for a standard deviation. Population parameters are the mu for the mean and the sigma for the population variability for the standard deviation. That distinction is important because the terminology may mislead you if you don't understand what is meant in the question. So it's important to distinguish between parameter and statistic. So we had parameters so far given when we did hypothesis testing. So when we compared the sample mean to a population mean, we had our sigma given, and with the given sigma, we basically estimated the standard error of the mean, which is sigma divided by the square root of this sample size that we've just done. And this allows us to characterize the distribution of the sample means, which is these randomly drawn samples, and they distribute in their means following a normal distribution, which is quantified or estimated based on the variability in the overall population. So now in the T distribution, we're doing something comparable, but now we don't have the standard deviation given. So the standard deviation of the population is not given for the T distribution, but we're utilizing the T distribution to essentially resemble this standard deviation or estimate this standard deviation. And this basically, so this actually comes from as a concept. So there was in the 19th century, there was the chef brewer of Guinness in the UK. They faced a problem. They had a quality standard that they wanted to meet. However, to test the entire output of a day, to estimate this variability, they couldn't just test every bottle of beer. So you need to reopen every bottle and you need to take a sample and you need to measure this. It's not doable, right? So they did experiments and they found out that the distribution from one batch of beer, if they take randomly one batch of beer out, like, I don't know, 6 cases or whatever quantity, and they take this variability within that sample, this variability can be used to extrapolate it to the variability of this met or not met quality criterion for the entire population of beer that was produced in a day. So that's actually the birth hour of the T distribution. As bizarre as it sounds, but that's how it actually found its way into population health, into medicine, into whatever field employing the same T distribution. And that's one of the most commonly used tests, essentially. Okay, so what you see here, that the larger the sample size, the more closely this resembles a normal distribution. If the sample size is smaller, it basically deviates a little bit, but it still kind of resembles the shape of a normal distribution, which essentially will lead us to a new concept where we actually need to, quote unquote, manipulate or modify our estimation of the standard deviation to really reflect the standard deviation of the population. And this is now, some of you may have done it wrong on the homework, which I don't think this time I took points for it. If you do a regular standard deviation, you're basically utilizing a different formula than is being used then for the population standard deviation. That was this distinction between stdef.p and stdef.s, or stdef is the standard function. Reason for that is because the calculation is different, because you try to estimate the standard deviation that it gets closer and it more closely resembles the normal distribution. That's why you need to standardize it for the so-called degree of freedom, which we will discuss in the following. So again, normal distribution for the entire population has a beautifully shaped, symmetric, unimodal bell-shaped curve. With 30 individuals, which is like this magical threshold, beyond which, if you have a sample size that exceeds 30, you usually get away with utilizing the set distribution. and using the Z-score table for the estimation of the percentages. If you have a sample size below that, you essentially need to use the T-score table. So you need to assume a T distribution. But the smaller the sample size, the less likely will nicely represent and reflect the normal distribution. So when the sample size increases, S approaches sigma, and T and Z become equal. That's essentially what I said in different words. So the T distribution is the distribution of differences between means. So it's only reflecting this distribution of the individual means of these samples to the population mean. The T distribution are calculated differently. As you remember from the standard deviation, we calculated the sum of these individual deviations squared. So this the sum of these squared deviations divided by the sample size. Now for the T distribution, we are dividing it by n-1, and this is the degree of freedom. So n-1 resembles helps to modify this calculation in a way that it more closely resembles the normal distribution. Conceptually, degrees of freedom are the number of entries in the knowledge of your sum of squares. Remember, this is the sum of squares. So these are the squared deviations summed. This is the sum of squares. So just the numerator here is sum of squares. In the knowledge of your sum of squares, you can lose one redundant entry, one X you can drop. So your last X in your row, or any random X in your row of data points that you utilized for the calculation of the standard deviation, you can drop for redundancy, because you know the sum of squares, you can drop one of these, and essentially it is this last entry that you have dropped is then a resultant of this arithmetic association between sum of squares and all the remaining entries in your data series. That's why it's being dropped. And this is why degrees of freedom are what we will be working with in the following. This includes the T distribution, includes ANOVA, includes then also all the other T tests that we will be doing. So again, degrees of freedom is n-1, with dropping one redundant unnecessary data entry in the knowledge of the sum of squares. So now this is essentially simple, and we have an example to do that. Well, it's essentially not a difficult example, as you can imagine. This is this example. But these examples are important because they basically resemble what potentially may be in your quizzes. Okay, so chapter 4, present the data mean number of sessions attended by clients at the University Counseling Center. We noted that one study reported a mean of 4.6 sessions, so that's our mu. Let's imagine that the counseling center hoped to increase participation rates by having students sign a contract to attend at least 10 sessions. So this is something that is often done in education. This is something done also in behavioral health. You have to empower an individual to actually do something which is good for them. You basically have them sign a contract. And this was also true here for the counseling session. So the students signed a contract with themselves, with the counselor, that they would attend at least 10 sessions. 5 students signed the contract, attended 6, 6, 12, and 7, and 8 sessions respectively. The researchers are interested only in the universities, so they treat the mean of 4.6 sessions as a population mean. So essentially what you want to do, you want to compare these individual entries of these 5 students to the population mean. So now the standard deviation is not given. Do you need to calculate the standard deviation? And that's how the exercise starts. So essentially, first thing you always do is the mean. So that's simple. So the average D4 to D8 gives you a mean. Then you calculate the x minus m. Calculate this deviation minus this. you basically have now your deviations. Now you do x minus m squared. That's also a simple calculation. Gets you then here to the sum of squares. And this sum of squares essentially is now where the calculation differs. So you essentially, if you calculate now the square root of this divided by the count of these 5 entries, as we formerly did, you get 2.27. But this is not how we're doing it, because we need to now utilize a new formula, which is now minus 8, but this minus 1 now. So this basically gets us now to that to this estimated standard deviation. So we're assuming this now to be our standard deviation, which should be resembling that standard deviation of the population. And just to confirm our thinking, we can now do STDEF.P. This is the 227. And now we do the regular STDEF. This gets us to 2.48. So that was the reason why I was sticking around with that STDEF.P versus STDEF.S, because this is basically an entirely different formula, right? This is a different concept. The actual estimate is not that much different, but conceptually it makes a huge difference. If you have a large sample size, this difference will be even accentuated. So it has a lot of weight conceptually. So this is now STDEF.P, this is STDEF.S. So these two are important to keep in mind. What are we going to do next? So we want to compare now. So we know now we have a population of 5 individuals, and we know based on our estimated standard deviation, we can now estimate our standard error of the mean. So what will this distribution be? So this is simple because we're having this standard deviation now divided by the square root of the sample size. And this is already where a lot of mistakes happen, because this calculation is now done with the sample size. So the n-1 you only use for the calculation of the standard deviation and not for the calculation of the standard error of the mean. And that's important. I've seen that being mistaken quite often. So please remember that. Good. So based on this, we can now obviously also calculate our confidence intervals, right? We can also determine now our critically set score. So what is our alpha? Let's say our alpha is 5% as usual. And this is where we're getting now to a new table. And this table looks different than the previous one. Same concept applies. We have percentages. Oh, don't download it. Let's go. No. So I downloaded it. No. So you have on the module, you have the examples, you have the PowerPoint presentation, and you have a T-score table. And that T-score table is quite important because you will need to know how to interpret it. So there are Excel formulae, of course there are, but I spare you those because they're a little bit hard to digest, to be honest. So when you look at this T-score table, you have now in the rows a different parameter. This time in the rows, you don't have the set score, but you actually have it inverted in a way. So as you have noticed with the changes in the sample size, the t-distribution will resemble, or more likely look like a set distribution. So sample size matters. Sample size in the context of a t-distribution is not sample size, but is the degrees of freedom that we've discussed. Degrees of freedom essentially are reflected here in the rows, and you have here on the columns, you have the actual p-values. And that's different now, because essentially you see that one-tailed and two-tailed are essentially overlapping, right? But you have here with 0.05 and two tails, you have only 0.025 with one tail, because you have to see it symmetrically on a two-tailed. So your critical value essentially is positive and negative, but it's considered to be symmetric on both sides. Whereas on one tail, it's only on one side, but it's doubled, it's stacked up, this alpha, if you have an alpha of 5%. So if we go now from a p-value of 5%, and we're finding our degrees of freedom, which for a sample size of 5 is essentially 4, our critical t-value would be 2.78. Is that clear so far? Simple, right? As a concept. Yeah? Okay. I interpret silence as agreement. Okay, so we want to now calculate a 95% confidence interval. So we're going to find out numerically what are these actually critical values. So we know it's 2.78. So on our distribution, if we would follow the distribution and we assume it to be a normal distribution, so this is the calculation that we did. This is the t-score, standard error. We've calculated all of this. So the actual distribution looks like this. So we have degrees of freedom of 4. The normal distribution is essentially, again, symmetric, bell-shaped, two-tailed hypothesis testing. And here are our respective critical t-scores, 2.78. Easy, right? Not complicated. And now calculating a 95% confidence interval is easy. Well, 95% confidence intervals or the critical scores. The only thing we have to do with the same formula, so we have a sample mean of 7.8. So it's now 7.8 multiplied by 2.78 multiplied by our standard error of the mean. That would be the positive. No? Okay. Oh, yes. Okay, so our upper limit is 10.8 or 10.9. Now the lower limit, you calculate in the same fashion by basically taking the mean and subtracting 2.78 multiplied by the standard error of the mean. So 4.7 to 10.9. If the mean is 4.6, are we rejecting or accepting the null hypothesis that our m, so here's the H0, m equals mu, HA, m does not equal mu. At an alpha level of 5%, are we accepting or rejecting the null hypothesis? Rejecting, correct, we're rejecting because the 95% confidence interval does not include our mu. Therefore, we are rejecting the null hypothesis. And this is pretty much all that needs to be done. The last thing essentially is the formal calculation. So we're calculating our t-score, we're calculating our m minus our mu, which we have here, and we're dividing it by the standard error of the mean. Not much surprises here. We're getting a t of 2.87 that is greater than the critical t. Thereby, we're rejecting it on an alpha level of 5%. If we were to test a one-sided hypothesis, would we reject or accept the null hypothesis? Let's say we're testing. So this is two-tailed. This is one-tailed. Where the H0 would be m is smaller than mu, and the HA is m is greater than mu. Would we accept it or would we reject it? The null hypothesis. Any guesses? Any gut feelings? If you do a two-tailed test, is it more likely that you reject the null hypothesis, or is it less likely to reject the null hypothesis? Two-tailed more likely or one-tailed more likely? Two-tailed is less likely, because you have to distribute your 5% on both ends, right? So actually it widens the confidence intervals. You remember the conversation we had with, and this is conceptually important because it's the same but thanks for the topic, because you remember from last time. Yeah. We are actually getting more power, and this is on the midterm on Wednesday. Please review that. Do me that favor. So the factors that increase statistical power is by increasing alpha, turning a two-tailed hypothesis into a one-tailed hypothesis, increase the n, exaggerate the differences. So when you think about power, you can increase the alpha. So you make it from a 5% alpha to a 10% alpha. Thereby, you get more of this zone of which you're basically rejecting. If you turn a two-tailed into one-tailed, you have the same problem. Here you have alpha now on both sides, but basically that overlap of which you are significantly rejecting is basically larger. So the overlap between two population and the non-overlapping regions, actually increase, and the overlapping regions decrease. You can also increase the sample size, then you get this. So remember these points on power. Increasing the differences, same principle. You are getting them apart. You get a larger fraction of non-overlapping regions. Okay. Okay, so this is conceptually important to keep in mind. So we are rejecting now the null hypothesis, and thereby we're basically getting a significant treatment effect by having students sign a contract to attend the counseling sessions. So if they sign this contract, they're actually more likely to attend the counseling session. And by doing that, by asking each student to sign such a contract, you will actually overall in the population and all the students you're basically administering this intervention to, you will overall get the mean higher than the population mean. And thereby they will have better outcomes academically. So basically this is the same calculations we did now. So we came through the same calculations. We get the same standard deviation estimate. We get the same standard error of the mean. We're getting the same t-score. Now we're making decision to actually reject our null hypothesis. So when you calculate the confidence interval, it's the same principle as we have done with the set distribution. You have a mean. You calculate these critical t-values, the respective score, and that becomes your 95% confidence interval within which you're 95% confident to capture the population mean if you repeatedly draw it. In our case, this was significantly different from the population mean. So here we have 2.78 minus 2.78. So it's here for 4.71 and 10.9, just as we calculated. And yeah. So the interpretation of this confidence intervals is the same. Include each of these estimates of the population mean 95% of the time. 5% would be either above or below. Then in the same fashion as we did previously with the set distribution, we can also calculate the effect size. This is done again with mean minus the mu divided by the standard deviation rather than the standard error of the mean. To basically take the effect of the sample size out of the equation and shift it back a little difference. Cohen's d, the conventions are the same. 0.2 to 0.5 is a small effect size, 0.5 to 0.8 is a large effect size, and greater than 0.8 is a large medium effect size. And greater than 0.8 is a large effect size. So for our example here, it's basically effect size can simply be calculated as our mean minus mean divided by our estimated standard deviation of 2.49. That's an effect size of 1.28, which is as per Cohen's conventions, small, medium, or large. 0.2 to 0.5 is small, 0.5 to 0.8 is medium, greater than 0.8 is large. This is a large effect size. Okay. So this was this example, then we have here a second example, which we also can do quickly. Let's apply the new formula for standard deviation to a familiar activity. Multitasking employees were observed at one of two high-tech companies for more than 1,000 hours. The employees spent just 11 minutes on average on one project before being interrupted. Moreover, after each interruption, needed an average of 25 minutes to get back to the project. So maybe the reality is that multitasking actually reduces overall productivity. Suppose you were a manager of these firms and decided to observe a period from 1 to 3 each afternoon during which employees could not interrupt one another, but might still be interrupted by people outside the company. Test intervention, you observe 5 employees and develop a score for each time spent on the selected task before being interrupted. Here the factual data, 8, 12, 16, 12, and 14 minutes. In this case, we took 11 minutes as the population mean. So that basically is the time test intervention to develop a score for each time spent on a selected task before being interrupted. Okay, so we have a population mean of 11. We have 5 employees and 5 different scores, which I have here on the side already arranged. So we have a mu of 11. Same concept again, so we're calculating the average. We're calculating and estimating m. We're calculating here a standard deviation, which is simply STDEF of these 5 entries. So that's our SD. Based on that, we calculate now standard error of the mean, which is essentially this divided by square root of yeah 5 employees, right? Square root of the sample size. We have 5 employees, so that's our standard error of the mean. It basically gets us now in the same situation as before. So the only thing we need to do, we need to understand what's our alpha, which is 5%. Based on that alpha, we can now determine with our sample size of 5 and our degrees of freedom of 4, we can determine this critical T. It's again 2.78. It's 2.78. Based on that, we basically can continue now to calculate our 95% confidence interval, which basically would be so 95% confidence interval again, lower limit, upper limit. With the lower limit is basically being the mean, our sample mean, minus 2.78 multiplied by our standard error of the mean. The upper limit being our mean plus 2.78 multiplied by our standard error of the mean. We're seeing now a 95% confidence interval from 8.7 to 16.1. And we want to know whether this is significantly different from our mu. If our null hypothesis is m equals mu, which A is m not equal to mu, so are we accepting or rejecting the null hypothesis? Yeah. We're accepting the null hypothesis, correct. Because the T that we will calculate is not exceeding our critical T. So I reiterate the key to these quizzes that we will be facing on Wednesday to some extent, but really then for fun is to read the question and deduct and extract the main information from that question, whether this is a normal distribution or population where you have the standard deviation given, or it's a sample which you actually need to calculate the standard deviation from to estimate the population standard deviation and utilize for your further calculations. So this being said, we're calculating now our T. The T is now our mean of 12.4 minus our mu of 11, dividing it by the standard error of the mean. We're getting a T of 1.1, which essentially does not exceed our critical T, so we're accepting null. And now we also calculate the effect size, which for obvious reason needs to be also small. So we're calculating our mean minus our mu and dividing it by the standard deviation of 2.97. Gives us an effect size of 0.47, which interestingly still is a medium effect size, but due to the large variability, does not result in, with the small sample size, and the large variability still results in a non-significant result. Good. Any questions? It's a fairly easy chapter. That's like we're coming from hypothesis testing, and we just came from the confidence intervals. It's kind of a stroll in the park to make this transition. The only caveat really is that transition from the population to the sample. That you conceptually just understand the concept of degrees of freedom that are being used to estimate the sample size, the standard deviation, rather than having it given from the population. Good. This being said, let's quickly go against statistical power. Okay, so we remember the confidence intervals. We remember how it's being calculated. We're remembering effect size and why it's being calculated. Basically, you get a set score that essentially is associated with the difference divided by the standard error of the mean. So you're characterizing and standardizing now the differences between your sample mean and your population mean. You divide it by the standard error of the mean, which is the estimation of the variability of your distribution of the sample means. And the problem with that is that the standard error of the mean is strongly affected by the sample size, as we have seen right now in our example. Because of the low sample size, we have not seen a significant difference. Although 12.4 versus 11 could, with a large sample size, still be a significant difference. So this is essentially in our last example that's actually reflected why it's so important to remove the effect of the sample size, because the difference of 11 versus 12.4 is actually not that small when you think of it in terms of a difference of a population difference. So by taking out the sample size out of the equation and quantifying the effect size and the differences that characterize the effect size by the standard deviation and not by the standard error of the mean, you get a standardization that is independent of the sample size. So again, keep in mind, so you have the effect size determined the mean differences, and the difference plays a major role with the same variability, logically, or alternatively, as the changes in the numerator and not the denominator, you also have differences in variability. So you have the same difference, but equal variabilities between both groups, but they're smaller in your overall population comparison. You essentially get larger standard deviations. So therefore, characterization of the effect size to characterize your differences are essentially allowing you to take the effect of the sample size out. These are the conventions that we've talked about before. To quantify the effect sizes, you're quantifying that overlap between your populations. And this is where variability plays a role, because these overlaps are obviously driven by the variability of these samples. So the calculation of the differences by the standard deviation gets you to the effect sizes. Meta-analysis is basically an amalgamation of all these effect sizes, where you basically compare effect sizes across several studies. You basically find one overarching effect size that basically represents the effect size of one particular intervention that has been the common denominator of all these studies. So what you've seen, and we've talked about this last time. Keep in mind differences between a type 1 and a type 2 error. Please don't mix those up. Type 1 error is that error that you make when there's no effect. You are finding an effect. So that could be various reasons why you find that effect, but keep the difference to a type 2 error in mind. What the type 2 error is basically, you have an effect, but you miss finding it. That's usually a sample size problem, because the factors that affect statistical powers are increasing the alpha, so accepting more type 1 error. So in a two-tailed hypothesis and a one-tailed hypothesis, increase the n and thereby change the variability or exaggerate the mean difference by intensifying your intervention. So if you increase your alpha, you're basically increasing that region of acceptable type 1 error. So you're basically increasing this non-overlapping error as compared to the 5% alpha. If you shift from a two-tailed to a one-tailed hypothesis, following your overall hypothesis in your study, you do the same thing. So you're shifting your type 1 error, your acceptable type 1 error from both sides, from the side that you think is least likely. You're shifting it to one side, and you basically stack the 5% up on one side only, usually the larger non-overlapping region, which constitutes the power. By increasing the sample size or decreasing the standard deviation, again, you increase that area that is non-overlapping and is exceeding that critical value on the right tail, thereby giving you more power. Or you can increase the difference between the means. And this is unfortunately also often not possible. So the most important thing that you can modify in most cases is the sample size. And that is really the key in study design, because understanding the sample size will basically allow you to conduct an adequately powered study, which is essentially what every researcher is striving for. So that's why this is very important. All right. Any questions concerning the midterm? Another example, or you want to use the time to study for the midterm? Good night.
Thank you.
Question from you?
No, I just said thank you.
Have a good evening.
Good night.